Thank you very much for the invitation. So I will try to say a few things about the master field. One master field on the plane. I will start by describing the master field without explaining where it comes from, and then I will explain something about where it comes from. So it will look very elementary. And so I'm working on the plane, which is the Euclidean plane R2. And it has, well, it's a space where we can measure lengths, we can measure areas, we can do usual geometry. And we can draw loops on R2. And I will describe a function on the set of loops on R2. So I take a loop on R2, I draw a loop, and to this loop I associate maybe a complex number. Well, it will turn out to be a real number. And there is a theorem. And the theorem is there exists a unique function, which I call phi, like field, capital phi, like master field maybe, from the set of loops on R2. So let's say to the set of complex numbers, although it will be quite clear from, well, it could be, I'll say a word about the range later maybe, which satisfies the following 5 properties. In stating the theorem, I will prove, well, I will explain uniqueness. Existence will be maybe the second part of the talk. Maybe I should say a word about what I mean by a loop in R2. So a loop is a continuous curve, starting somewhere and coming back to the starting point. Continuous, it should have finite length. That's the assumption I want to have. So technically, I'm looking at rectifiable or loops with finite length. And well, we can think of many ways of associating a number to every loop with finite length. For example, the length. Or something else would be the area enclosed by the loop. It turns out that this area is finite. It's not obvious, but it's true. It's neither the length nor the area I'm interested in. It's another function. So how am I going to describe this function? Well, first I want to say that this function is continuous. Continuous with respect to which topology on the set of loops? Well, I say that a sequence of loops converges if say it converges uniformly for some parameterization, or say uniformly for arc length parameterization. You can parameterize loops at constant speed. So I say that the sequence of loops converges if with this parameterization it converges uniformly and the length converges. That would be convergence in one variation. That's somehow a natural topology on the set of loops with finite length. Okay. I want to describe a function which is continuous. I do not need to define it at every point. I only need to define it or to explain to you how it is measured, how it is defined on a dense subset of loops. So I will only try from now on to describe what is the value of this function on loops which look like this. Say they are very nice and they intersect themselves in very nice ways, not too often, that is finitely many times, and they come back to their initial point. That is a very nice loop. No triple intersection, no nothing. Everything is generic and finitely many intersections. If we know the value of phi on all these loops, we know phi entirely. But there still are quite a lot of such loops. So the second property of phi is that it is invariant under area preserving diffeomorphisms of R2. Now that is a very strong assumption, because it means that if I apply to this loop an area preserving diffeomorphism, I continuously change the picture, but I preserve the areas. Well, what areas are there here? They are the areas of the faces which the loop defines on the plane. So this phi on this loop will be the same as phi on this loop, provided the faces have the same, the corresponding faces have the same areas. That reduces the scope of the problem drastically, because now we are facing essentially a combinatorial problem. It would probably not be very easy to say to produce a very nice encoding of a loop like this, but sorry, I'm going too fast. What we only need to know to compute the value of phi at this loop or that loop is the discrete combinatorial way in which the loop intersects itself. So there is a loop, then it comes back from the left, and then from the right, or whatever, and this face has such area, and this face has such area, and so on. So this is a finite dimensional information, so to say. Now, I don't know if the picture is very convincing. Well, it's, now my point of view is that given the combinatorial structure of the loop, the way in which it intersects itself, and the shape, well, not the shape, sorry, the combinatorial structure of the self-intersection of the loop, whatever this exactly means. As I said, I would not be able to produce a nice encoding of this structure, but I think we see what, I hope you see what I mean. Phi of this loop is a function of the areas. It is a function of 1, 2, 3, 4, 5, 6, 7, 8 positive real numbers. And I want to focus on all the loops which have that combinatorial structure, but with possibly different areas. And I want to describe the value of phi at these loops as a function of these areas. And in order to explain to you how to compute this function, I will write down a differential system. I will explain to you how to differentiate the value of phi with respect to the area of one or the other of the faces which the loop produces. So I want to explain how phi varies when I inflate a face or deflate a face, or that kind of transformation, without altering the global structure of the loop. So we want to have a kind of differential equation. We need an initial condition, and the initial condition is that phi of the constant loop is 1. And starting from there, we can start inflating the faces, because any loop from which you deflate all the faces to the point that they have no area at all left is a constant loop. And then you can inflate back to recover that particular loop you're interested in. Okay, now we really have to go into more specific things because there are only two properties left. So the fourth property will tell us what happens when we inflate a phase which is adjacent to the unbounded phase, which is at the boundary, well, which is adjacent to the unbounded phase. There is an exterior, and so this phase, for example, is adjacent to the unbounded phase. This phase isn't. It doesn't share an edge with it. Sharing a vertex is not good enough. So I can write this in this way. Somewhere in the loop, I see a piece of the loop which is like this, and here there is a face of finite area, maybe area S, maybe I'm looking here and I see a face of area S here, and on the other side I see a face which is the unbounded face, which has area, infinite area. And what I want to know is what is d over ds of this. I change the loop only by slightly inflating this phase. Well, this is very simple. It's minus 1/2 of phi of the same loop. So I am glad to inform you that we can already compute the value of phi on some loops. For example, we can compute the value of phi on this loop. Because we know the value of this when so this is a function of s. When s equals 0, by the third assumption, this is 1. And when we differentiate with respect to s, we find minus 1/2 of the same function of s. And this is fairly easily solved, and find e to the minus s over 2.
You're not allowed to vary more than one face at once.
You might vary several faces which all are adjacent to the unbounded face by taking them one after the other. In the fifth property, we are going to change several areas at a time, but in a very rigid way. So it is not that flexible.
Excuse me, do you count the area with the sort of oriented area?
No, thank you. That's a very good question. No, the area is a positive number. The orientation is taken care of in a different way. So, but actually, if the arrow was in the other direction, we would have the same equation. So the orientation, well, that's true, but it is also true that the same loop with the other orientation has the same phi of that loop is also e to the minus s over 2. Thank you. Actually, I think I should include it here. So this is slightly misleading, if not wrong. Now the fifth property has a variety of names, because of course this is where most of the information will be. So in this setting, it is called the Makiyenko-Migdal equation. I think that in this framework, it was discovered by Makiyenko and Migdal in the 70s. It is an instance of Schwinger-Dyson equations, which means, I believe, that these equations, the equations which I am going to write, can be obtained from the system which gives rise to this mysterious function phi, from an integration by parts in a path integral. So they are a manifestation of the result of an integration by parts. And actually that's how Makiyenko and Migdal found these equations, by performing an integration by parts in functional integral. I think some people also call them loop equations. equations or okay, so what do they tell us? So we are going to see what happens when we vary the areas of faces which are not adjacent to the unbounded face, because this is already seen. And we are, well, the Machiavellian equations involve varying the areas of several faces at a time. And we need to choose a vertex. So we choose a point of self-intersection. So for example, this one, it is too small. I have to do another picture. So somewhere we see this. And there is a point of intersection, and there are two strands of the loop which cross at that point. And here, there are several ways of looking at the point where there is a self-crossing, but I want to look at it in such a way that the two strands are oriented upwards. Now, around this vertex, there are four faces, and they have areas T1, T2, T3, T4. So, for example, around this vertex, these four faces are these four faces. And the equation is that if we...
So that point is not on the boundary, or that can be on the boundary?
It could be on the boundary. It is possible that one, or in fact two of these faces are infinite. So I will say in 30 seconds what you do if one of the faces is the unbounded face. But generically, you take the alternated sum of the derivatives with respect to the faces, plus minus plus minus. So you inflate these two faces and you deflate these two faces. And that is equal to the product of the values of phi on two new loops, which you obtain by erasing the intersection point and reconnecting the strands in a new way. Well, if you do this, so I'm erasing the intersection point and I am reconnecting, I didn't check how I should look at it in the first place. So here, okay. So I'm erasing it and I connect the two strands in the other way, which is compatible with the orientations. I take the first incoming strand and I connect it with the second outgoing strand, and I do the same for the two others. And in doing this, I produce not one but two loops, and I take the product of the values of phi on these two new loops. So we had this, but now we connect these two strands together, and you can check that this is indeed a loop, because in the initial picture, we don't know exactly what happens around this part of the picture, but what we know is that we have only one loop. So if we follow the loop starting from here, the next time we come to this intersection point is not through here, but through here necessarily. Otherwise, we will have two loops. So we connect these two strands, that is a loop. And we take the other loop, which is here. So it may happen that some of these faces are the unbounded face, in which case you should just ignore the derivative which is there. You cannot inflate or deflate the unbounded face. It may happen that actually two of these faces can be the same. For example, if I consider this loop, there is only one intersection point. And these two faces are the same face, in fact. Locally, this is not obvious, but they are connected. Well, it doesn't matter. You take twice the derivative. You take it twice. So, for example, let me compute the value of phi on this loop. So this loop is the next simplest loop. It has two faces, areas S and T, and phi of ST is a certain function which I will call f of S and T. We know that f of 0, 0 is equal to 1. We know that the derivative with respect to f is minus 1/2 of f, because differentiating with respect to S is differentiating with respect to a face which is adjacent to the unbounded face. And if we apply the Machiavellian equations at that vertex, we find that d over ds minus d over dt plus d over ds minus 0. So twice. So this particular combination of partial derivatives of f equals what we get by erasing the intersection point and connecting again the strands in a different way like this. So now there is the yellow loop and the red loop. And the very nice thing is that we know the value of phi on the red loop and we know the value of phi on the yellow loop because they are just instances of this formula. We removed the intersection point. That's why this formula is effective, because it gives you an information of the value of phi at a certain loop in terms of the values of phi at simpler loops with fewer intersection points. So here we find the red loop e to the minus t over 2, because the red loop surrounds a face of area t, and the yellow loop, one has to be slightly careful, the yellow loop does not surround a face of area S, but a face of area S plus t. Now this is solvable, and we find f of st is equal to e to the minus s over 2 minus t times 1 minus t.
Why it cannot be done on the sphere? Simple.
You can consider a function with these properties on the sphere. The issue is, are we sure that we have enough information to determine the value of phi? We know only very specific combinations of the derivatives with respect to, well, phi is a function of several variables. On the plane, you can prove that what we have access to, for example, if we want to compute the value of phi on these loops, on this loop, we know the derivative of phi with respect to the area of this face, of this face, this face, this face, and this face, and this face too. And we need to know the derivatives with respect to these two faces. And what we know is for each intersection point a certain combination of the derivatives. And it is possible to prove that they determine the derivative of phi with respect to, well, they give us enough information. I think that on a sphere, the problem is that something is missing in the information. But I agree that this is something to be investigated.
I mean, if you take a simple look like this on the sphere, what should be the value?
I don't know what should be the value. I could express it in other ways, but I don't know the value in advance. I expect it to be much more complicated than this one. But well, So I think uniqueness of phi is more or less contained in the statement, because the statement explains how you compute phi. If it exists, there is only one way it can be defined. The 2 points being, the fifth rule gives this combination of derivatives in terms of values of phi on simpler loops. So you have a process by induction. You compute first on the circle, then on loops with one intersection point, then on loops with two intersection points, etc. So you have a kind of triangular array of equations. And the second point is that we do have enough information, although I'm not proving it, in these 5 equations to determine all the partial derivatives of phi with respect to the areas. Okay, good. I think it's clear too from the description that it does not take non-real complex values. This is purely real. This is a purely real story. So in fact, phi takes only real values. It's probably less obvious that it is in fact bounded by 1, but it is true. Okay, okay, I have to erase the thing. So what is this function phi? Well, this function phi arises from a large n limit of un.
Let me ask you a question.
Sure.
About the, so you are going to prove the theorem, or you just want to? No. But the theorem stands by itself. So given the conditions, you can prove it exists. So it means that if you start from one part of the diagram, or from another part, you are going to end up with the same function.
Yes.
I mean, I'm forget for a minute about the UN thing. In terms of the theorem, so you give yourself a loop diagram, and then the question is whether you can construct the function just by iteration, starting from any part of the diagram.
Yes. Are you worried about possible inconsistencies if you split different vertices in different orders?
Yes.
Yes, that's true. It's not actually. It's another problem. Yes. Yes, that's a non-trivial part about existence. It might be that when you differentiate by splitting vertices in a certain order, you find something different from what you find with it. So in fact, I didn't prove I didn't prove. Yes, I proved uniqueness. I certainly didn't prove existence. Yes. Yes, existence boils down to proving that if that something is independent of the order of the vertices. Is that what you're saying? Yes. Well, this theorem doesn't exist in a sense. I mean, it doesn't appear in the paper, but it's a nice way of explaining. Well, at least to me, but okay. So let us think about UN now. So this function phi arises from the large n limit of the UN Young-Mills measure on the plane in this case. And as some of you noticed, this could also be investigated on other spaces, and in this case in other two-dimensional spaces where the Young-Mills measure is defined. So, for instance, on the sphere, where very interesting things happen, but that's another story. Okay, so what is this Young-Mills measure on R2? I am trying to estimate how much I should say about it.
People here are very familiar with these things now.
Okay. So, so maybe you have questions? Okay, so let me very briefly give a geometric picture of where this Young-Mills measure comes from. It seems that in physics today, when you want to describe particles, elementary particles and their interactions, you are working on space-time, which is a four-dimensional Lorentz manifold, and over that manifold there is a principal bundle, which is quite mysterious, but it seems to be there, and that means something which locally looks like M cross some group, and that group will typically be U1, U2, SU2, SU3, a nice concrete matrix group. And what group you consider tells you what kind of physics you are doing. Electromagnetism, weak interaction, strong interaction. And well, Young and Mills, well, this is a very long story, so it so happens that so sorry, let me say this again. If you want to do electromagnetism, the group you are going to take is U1. Don't ask me why. If you want to describe weak interaction, which is another kind of interaction, you want to take G equal SU2. Strong interaction, SU3. And this interaction is mediated by fields, and these fields mathematically are described by differential forms on space-time with values, with matrix value differential form, with values in the Lie algebra of the group you've chosen. This, in the case of electromagnetism, this A is the vector potential of electromagnetism, which, according to the theory, is more fundamental than the electromagnetic field itself. One should really think of the potential as the nice object rather than the field. So the electromagnetic theory was investigated until, well, I mean, was understood by the 1940s maybe, and then Young and Mills in 1954 suggested that a similar formalism could be used to describe other kinds of interactions. That means that for the theory of weak interaction or the theory of strong interaction, there are fields which play the role of the electromagnetic potential, and they have the same geometric structure of a differential one form on space-time with values in the Lie algebra. And Young and Mills produced, or at least there is an action which is now named after them. And the Young-Mills action is something that takes one of these fields, one of these interaction fields, and produces a number. And this is, the one half is maybe cosmetical, but let's have it. Integral over M of, say, trace of F material star F, where F is a two-form defined by dA plus A comma A. Well, depending on how familiar you are with these notions, you can take this more or less poetically. And I think even if you are not very familiar with these notions, something of the structure is can be apparent on the formula. So, for example, you see that S of A is a quadratic form of this F, which is itself something linear plus something quadratic in A. So the energy we are interested in this theory is a quartic function of the vector potential, of which I said that it is the fundamental object. Another interesting feature, without going too much into details, is this star here. This star is the Hodge star operator. And this is the operator which exchanges k-forms and n minus k-forms on an n-dimensional space, given some geometric structure. This is the only place in this expression where the geometry of the base space-time plays a role. Everything else is purely differential, is purely given by the smooth structure of space-time. I'm sorry, I don't know how much you can follow with my explanation, but this star depends on the choices of a particular structure on M, and in general it depends on the choice of a metric, well, a Riemannian or a Lorentzian. It so happens that if n equals 4, this star operator is conformally invariant, meaning that it depends on the choice of a metric on spacetime, but two conformal metrics will produce the same Hodge operator, not in general, but the same Hodge operator between two forms and two forms, because 4 minus 2 equals 2. And if n equals 2, this is not a situation where things are a bit particular. We are using the Hodge operator to produce a 0 form from a 2 form, and that only depends, well, that does not depend on the whole metric, it only depends on the Riemannian or Lorentzian volume. Or on the area, because we are in 2 dimensions. So this vaguely explains that 2-dimensional Yang-Mills theory is a theory which is invariant under area-preserving diffeomorphisms, just as the function phi was. And 4-dimensional Yang-Mills theory is a conformal theory, but I have nothing more to say about 4-dimensional Yang-Mills theory. And so there are these fields A. There is this energy S. When you have a field A, you can compute the energy S of A, and this is this non-negative real number. And from this setting, you can ask, what is there a way of choosing a connection at random in such a way that the probability of a measure of a connection will be proportional to e to the minus s of a? So is it possible to define a Boltzmann measure on the space of fields A corresponding to this energy or action S? Well, I shouldn't use energy for action, they're not the same. So the Young-Mills measure is a probability measure which corresponds to the problem of choosing at random a field, a gauge field A, according to the Boltzmann measure corresponding to this Young-Mills action S. I will not try to go continuously from there to the mathematical object. I think I will jump into something less fuzzy and more concrete. So this blackboard should be thought of as an inspiration, and the relation between this and what I am going to explain now will maybe not be obvious, but that's something we can also discuss later. So let me take a surface sigma, well, let me call it M. That is R2 or a sphere or something more complicated. And that will be our space-time, two-dimensional. Let me take a group, and we have in the back of our minds that this group will be UN or maybe ON or a nice matrix group. On the surface, I will describe a kind of statistical physics model, which is the following. I draw a graph so this is on the surface M, maybe it's a sphere, maybe it's... I want the graph to cover nicely the surface. So this graph is a set of edges. And the edges of this graph are not abstract edges, they are very concrete edges drawn on the surface. It is really a graph drawn on this surface. In terms of the particles, these edges are the path which the particles can possibly follow in space-time. And when they do follow such an edge, their state is modified, and is modified by the action of an element of the group. But okay, so we have a configuration space. Let me choose an orientation for each edge. And the configuration space is G to the power E. So, I am describing a statistical physics model in which I have a surface which I cover with a graph, and the configuration of that system is an element of this space. That means one element of the group, one matrix, one unitary matrix for each edge of this graph. And this unitary matrix tells you how the state of the particle which goes along that edge is modified when it goes along that edge. This corresponds to this field A in a way which I'm not going more into now. I want to put a probability measure on this configuration space. There is a way of choosing at random a configuration which is just taking each matrix uniformly at random and independently of each other. Because G here is a compact matrix group, it has a very nice invariant probability measure, and we could take the product of Haar measures. That would not be a very interesting model, but that is a model which exists and which actually some people work with for some problems. But we want something different here, because we want something which takes in some way this action into account. Whenever I have a path in the graph, and whenever I have a configuration, I can multiply the matrices which this path sees, and in the way it sees them, and possibly taking inverses of these matrices if we go along the edges in the wrong direction. So if we have a path C, which is a product of edges E1, En, with maybe signs indicating that we are going backwards, there is a function which goes from the configuration space to the group, which takes the whole configuration and yields just the product of the matrices which yes, I didn't know G. Just the product of the matrices which the path sees in the order in which it sees them, with possible inverses if needed. Okay, let me take another look at this action here. I said that it is quartic in A. Well, for some reason, this is a problem, but superficially it looks quadratic in F. And let us stay with this idea that the action has something quadratic, and we are constructing a probability measure where a weight is e to the minus some quadratic functional of the object we are working with. So there is something Gaussian about this theory, and that's why in 2 dimension it is possible to construct the mathematical object. And so you will not be surprised that I introduce the heat kernel on G. T of G, that is the fundamental solution of the heat equation. Well, I have to choose to make a few choices to normalize this this heat kernel, but and with all these definitions, I can now construct an interesting probability measure on the configuration space. I declare that the probability dp of a certain configuration G is 1 over some normalization constant, which maybe depends on the surface and maybe depends on the graph, times, so here I write the product of Haar measures, and in between I want to put something which mimics in some way the action which is above, and this is a product of over all the faces I am looking at the graph and taking the faces of the graph one after the other, and for each face I can compute, well, the boundary of the face is a certain loop in the graph. I can multiply the matrices which I see along this loop which goes around the face. This is what I call H, boundary of F of G. This is an element of the group, and I want a number, and I evaluate the heat kernel at time the area of F on that element of the group, and that's it. So what do we have here? We have a surface on which, I didn't say it, but I should have. We are able to measure areas. That's the geometric structure we have. On that surface we draw a graph, a nice graph. The faces of this graph are disks. There is no funny face with a complicated topology in the middle. They are small, nice faces. This graph triangulates, well, it doesn't triangulate, but it represents nicely the topology of the surface. And we want to pick at random one, say, unitary matrix for each edge of this graph. And we want to do it in a way which is Gaussian in a sense and takes into account the area of, well, our ability to measure areas. And that is what this probability measure does. There is, well, it is based on the uniform probability on the configuration space. But a particular configuration will be extremely unlikely if any of these numbers is small. And when is one of these numbers small? Well, how does the heat kernel behave on the group? When T is very, so the heat kernel is something that for T equals 0 is the Dirac mass at the unit element, and then when T grows, it diffuses on the group, and after a certain time is essentially 1 because the Brownian motion, if you wish, on the group will fill the whole group because it is a compact group. So this is something which for small t is peaked around the identity element of the group, and for large t is essentially equal to 1. So whenever we have a face with a large area, this number is essentially 1, and this factor does not tell us much. But when we have a very small face, a face with a very small area, this is checking that the product of the matrices around the boundary of this face is close enough to the identity element of the group. Otherwise, this number will be very small, and this configuration will be discarded. So this makes sure that around small faces, the product of the matrices is close enough to 1. So that puts a strong kind of continuity condition.
Each edge appears twice, right? Each
Yes.
interior edge appears twice.
Yes.
So they also appear in the other heat kernels, in the other faces, right?
Yes.
At different times.
Yes. It's not very easy to express it in going from faces to edges. Well, there is some combinatory. Yes. But that's perfectly right. Each edge appears twice. Once for the face on the left, once for the face on the face on the right. Okay.
So when you multiply the matrices, is there a strain?
Sorry, the starting point.
Say more how each partial f g is defined.
Yes, there is a problem. If you change the starting point, you change the product, but you conjugate the product, and this is conjugation invariant. If you have a triangle like this, you have matrices A, B, C. If you start here, you will find A, B, C. If you start here, you find B, C, A, which is A minus 1, A, B, C, A. So any two choices will, so this is ill-defined, and the conjugacy class of this is well-defined, and this function is conjugacy is invariant by conjugation, because the Laplacian is invariant by conjugation on the group. Because we chose an invariant Laplacian, and I didn't say this, but okay, that was for one graph, and then so there are a few facts. The first fact is maybe not so important, but maybe it is, that this normalization constant does not depend on the graph. In fact, it depends only on the surface, on the topology of the surface. In fact, it only depends on the topology of the surface, whether it is the plane, a sphere, a torus with many handles, and the total area of the surface. And there are very nice explicit formulas for these numbers. And well, Witten certainly wrote them. I don't know if many people looked at these functions before, but Witten wrote them and used them for purposes of geometry, of problems of geometry. Another fact is that what we did for one graph, we can do for other graphs and for finer graphs. We want to do something on the surface M, not on a graph on the surface M. The graph was a step towards working on the surface. So we want to add edges and to refine the graph. And the good news is that when you do this, you produce new probability measures on new probability spaces, but all these probability spaces are related and they form a consistent family. And for this reason, you can essentially take the limit.
You have two G's, right? One is for the graph, the other one for the group.
Yes, absolutely.
So which one is here in Z, is that in your...
Oh yes, it also depends on the group, that's right.
So this is the graph here, right?
This is the graph, but it also
No,
depends.
no, of course, yes, but it's on the group.
This one,
It's for the graph.
does not depend on the graph. But on the plane, it does not depend on the group either, because it's equal to 1. But on any other surface, it does depend on the group, yes. And this is so consistent under refinement, and you can refine it and essentially take the limit. And there is a theorem, which I'm going to write. Well, yes, I'm writing it. What is the theorem? What kind of limiting object do we get? Well, there is a unique G-valued stochastic process which I denote by capital H because it's reminiscent of this, indexed by curves on M, such that for all graph G, if you look at the collection of random variables HE, where E has the set of edges of the graph, this has, well, when I say unique, it's unique in distribution. And this has the distribution PG, the one which is just there. And second, it is continuous. If Cn converges to C, say in one variation, then HCn converges to HC in probability. So this Young's measure is the following kind of object. You have the surface M, you've chosen the group G, you know how to measure areas on M, and for each nice curve on M, you have a random element of the group. You have a random matrix. So the process is the collection of all these random matrices. Yes, I'm cheating a little bit. Yes. But I think it's many of these random variables are not very interesting in this formulation because if you have a curve with distinct endpoints, the distribution is uniform. But I think this is not wrong, but I agree with you. It is a strange formulation. You want to have closed curves rather than open curves. Now let me relate this to the function phi of the beginning. Well, theorem, okay. For each n, consider the Young-Mills process, this process here, which I denote like this. On R2, I am working on R2. So for each, I am working on R2, and for each n, I construct the Young-Mills process with structure group UN. So if we choose n equals 5, we have a collection of a random 5 by 5 unitary matrices, and n equals 17. For each loop L on R2, I can consider this random matrix the trace of this random matrix, which I divide by the size of the matrix, and this converges as n tends to infinity, fast in probability, almost surely for any way you can couple these random variables, say in probability, but it is a good convergence in probability, to the deterministic number phi of n. And the function phi has all the properties that were stated in the first theorem. So, to summarize this, I will not write anything anymore. The kind of physics that is behind this describes interactions by means of differential one forms with values in spaces of matrices. And particles interact with these fields or feel the effect of these fields by having their inner state modified by an element of the group corresponding to this Lie algebra. And the Young-Mills measure is a kind of a random field, produces a random electromagnetic potential, random weak potential, random strong potential. So this theorem says whatever the group G is and whatever the surface M is, well, it is two-dimensional, that's of course a big restriction if you have physics in mind. There is a consistent way of producing this random field as far as the way in which inner states of particles are affected is concerned. And this says if you do this construction and let the size of the group tend to infinity, these random matrices, these random modifications of inner state, they converge in a certain sense, in the sense of non-commutative distribution, although it's not entirely apparent on this equation, but it is true. And that normalized trace has a deterministic limit, which is a number which obviously, by the way, is bounded by 1, and which can be computed, maybe not easily, but in principle, using the rules that I explained at the beginning. Okay, thank you very much.
We'll have a discussion later on with those who are interested, but is there already questions at this stage?
Just a naive question. What was done in physics? I mean, concerning this theorem, so people had this phi of L, or was it?
I don't think So Makienko and Migdal, they proved, they derived the equations. They invented the equations. So that's
which ones?
the fifth equation,
Fifth.
the main part of the theorem. So that's the striking thing. I mean, they took the functional integral, they do the integration by parts, some cuisine, and at the end there is the equation. Quite amazing. I don't think they really care too much about knowing if. I mean, this was somehow obvious, and they weren't entirely wrong in thinking that this was obvious, that there is that kind of convergence.
And the formulation was also made in terms of the heat kernel, or not at all?
So the appearance of the heat kernel in this two-dimensional Yang-Mills theory is usually traced back to Migdal, the paper of Migdal of 75-76, where he analyzes the Yang-Mills action and he writes the Fourier expansion of the heat kernel. And then this was taken again by Witten, who described the discrete theory. And well, then there was some mathematical work on taking the continuous limit of the discrete theory, seeing how it is related to the action and various limits, the large n limit, semi-classical limit.
So what was missing mathematically for being rigorous?
A definition of the measure to start with. I mean, Makienko and Migdal, they work with this functional integral, and they do these wonderful manipulations, but as seems to me at least to be quite frequent, each step is believable and everything is plausible. But you cannot make a rigorous argument by taking each step and making it rigorous. You have to go for a completely different way. In that case, it is because the starting point itself has no rigorous mathematical meaning. And so...
No, that I understand. But if you start with the formulation here, for instance, the one with the heat kernel, there's a real theorem to have a continuum limit.
Sorry?
What was missing there was the theorem on the...
Yeah, very well. They didn't use this theorem. But that's a typical theorem which is not interesting for Makienko, Migdal, Kazakov, Kostov. They would laugh, actually they laughed. Kazakov certainly did. When I explained this once to him, I mean, it's obvious. And so that's one of these things. There are a few technical issues here. I said that everything is nice and smooth. It is not entirely true, but it's as always. But maybe an interesting thing is that, for example, if you start from the action and if you say, I believe in Feynman integrals and I write the Feynman integral, and it is extremely efficient because it produces, for example, what Makienko and Migdal did, you somehow miss something, which is that the mathematical object which is described here is defined purely in terms of the heat kernel on the group, and this has nothing to do with the Yang-Mills action. The proof of this theorem has nothing to do with the Yang-Mills action. You take a graph, you take the heat kernel, you do manipulations, you take limits and everything. But then how is this stochastic process, or is this stochastic process related in any way with the Yang-Mills action? That's a question which arises because you have a rigorous proof of the existence of the process, which is not the formal object part integral. And in that case, the answer is yes, as we proved with James some time ago. that you can relate in a rigorous way this stochastic process to the Yang-Mills action, but that, I mean, in that case, maybe having a rigorous statement is the source of an interesting question and potentially interesting result. What do you think?
Maybe
Sorry.
Can you motivate the trace there at all? I mean, is that this kind of uniquely interesting function of this process, which?
No. That's well, what about the determinant, for example? You might ask. So these are unitary matrices. We are working up to conjugation, and a unitary matrix up to conjugation is exactly the spectrum of this matrix. If you know not only the trace of a matrix, but also the trace of the square of this matrix and the cubic power, you know the eigenvalues. So what is hidden here is the fact that if you have a certain loop and you want to understand the holonomy along that loop, okay, this gives you the trace of that matrix. But you can apply the same result to the same loop traced twice, and then you find, okay. So in fact, this contains convergence of all the moments of these matrices because of this multiplicativity, which I did not really explain. But otherwise, it would be only a small part of the story.
That was exactly my question.
So
But
my
I guess,
answer
I
is
guess
the
then,
same.
okay, so now you're controlling, say, the law of some limit of the law of the holonomy of a single loop that this measure associates sort of random joint law on different loops, right? So can you say something similar about, say, trace of a product of holonomy along? Right?
Yes. So of course, if you have these joint loops, they ignore each other. I mean, in the limit, they're independent. Actually, on the plane, they're not even in the limit. If you have one loop here and one loop there, that's fine. But if you have loops which, but then the equations are still true, and the limit still exists. So the theorem is true if you take here products of loops with there is a certain function here of several loops which plays the same role for a collections of loops. And it also satisfies these Machian-Comigdal equations. But in that case, the Machian-Comigdal equations do not always contain enough information to allow you to go down this recursive process. And no, sorry, they do not contain enough information to compute all the partial derivatives. So the algorithm, the theorem is true, but the algorithm to compute the limits does not work as well as in the case of a single loop.
So you can show that the derivative equations are satisfied, but that you can't, they don't determine that.
Yes, that's. I think that's it. I think that's what I'm saying.
So do you have a formula even for the n loops functions, or in fact there is no algorithm to compute them? Or do you mean that Machian-Comigdal equations are not enough? But there is one. Or
That's what I seem to mean, but I want to imply this. I'm a bit puzzled. Maybe after a cup of tea, I can answer the question.
Okay, let's thank Thierry again.